Good morning, students. In this lecture, I'm going to discuss the ionic polarizability and dipolar polarizability. So, in ionic substance, there are cations and anions. For example, we consider sodium chloride, which is an ionic substance in which there are sodium and chlorine ions, chloride ions. So, in a presence of electric field, the all sodium ions they tend to move in the direction of electric field, and then chloride ions they move in opposite direction to the electric field. As a result, there is a induced dipole moment in the ionic crystal. So let x1 be the sodium ion that displaces to the right, and x2 be the chloride ion that displaces to the left. So the relative displacement is x1 plus x2, which is a relative displacement between sodium plus and chloride minus ions. Now the induced dipole moment in a induced dipole moment in a sodium chloride is charge times x1 plus x2. The ionic polarizability is a relative displacement. It is a relative displacement between two opposite ions. So this the restoring force acting on cation and anion or same. So we write F is equal to beta times x1 and beta times x2. So here beta 1, beta 1, 2 are the force constants, b1, b2 are the force constants. The restoring force is same, therefore x1 can be written as F by beta 1, x2 can be written as F by beta 2. Therefore, the induced dipole moment P is equal to E times x1 plus x2 is E times F by beta 1 plus F by beta 2. So therefore, P is equal to E times 1 by beta 1 plus 1 by beta 2 times F, where F is equal to E times capital E. So therefore P is equal to E square 1 by beta 1 1 by beta 2 times E, where beta 1 is small, let us say capital M omega naught square, and B2 is small m omega naught square. So therefore P is equal to E square, and then we can take omega square, therefore we get 1 plus m E. Now we compare this with our definition of dipole moment. Induced dipole moment is proportional to the strength of the field. So where P is now in this case P is equal to alpha times E, where alpha I is ionic polarizability. So therefore when we compare these two equations, we get alpha is E square by omega naught square, 1 by m plus small m. The capital M is the cation and the small m is cation, and omega naught is the frequency with which the cations and anions oscillates. So, and E is the charge of the ion, and then now we look at orientational polarizability or dipolar polarizability. So actually we know that a water molecule is an example for permanent dipole. So in water has OH bonds. The geometrical arrangement of OH is such that there is a permanent dipole moment in the water molecule. So water is a dipolar substance. So in a dipolar substance, there are permanent dipoles, but they are randomly oriented, so that the net dipole moment in a dipolar substance is 0. The net dipole moment is 0 in absence of a field. So now in presence of field, the dipoles tend to align in the direction of a field. So we have a dipole. We know that there is a positive and negative charge, and when it is placed in a uniform electric field, they tend to rotate in a plane. So this gives rise to a torque that is perpendicular to the plane of these two charges. So this will be R cross F. The torque acting on this dipole will be R cross F. So the force acting on this positive charge would be pointing in the direction of electric field, but on negative charge it will be opposite. So the net force in a uniform electric field is finite. As a result, the dipole tend to align in the direction of electric field, and therefore the potential energy stored in the dipole in presence of electric field would be minus P dot E, where P is a dipole moment, E is the external field. So V is the potential energy stored in the dipole due to the presence of electric field, and where theta is the angle between electric field and dipole moment. So in this case, the polarization is dipole moment actually points from negative to positive. So V is equal to minus PE cos theta, where theta is the angle between E and P, where E is electric field, P is a dipole moment. The probability of finding a dipole along a theta direction follows a distribution f of theta is equal to exponential of minus V by kT. So where V is the potential energy, therefore f of t is equal to exponential of Pe cos theta by kT, where k is a Boltzmann constant and T is the temperature. So this is a Boltzmann distribution. This distribution is called Boltzmann distribution or distribution function. So now the probability of finding a dipole pointing along theta direction follows a distribution function f of t is equal to this. So the average value of x component of x component of a dipole moment is simply px average value. We can write it as integral of the x component of p is p cos theta at times f of t into solid angle divided by f of t into d omega. So this is the average value of x component of dipole moment. So, and all the dipoles in a solid angle is d omega. D omega is a solid angle which is 2 pi sine theta d theta. Okay. Now in a sphere, the solid angle actually theta goes from 0 to 1. So here we put 0 to pi, basically 0 to pi. So we rewrite this px is equal to 0 to pi p cos theta into e power pe cos theta by kt into 2 pi sine theta d theta divided by integral of 0 to pi and then exponential of Pe cos theta by kt 2 pi sine theta d theta. So let beta or u is equal to Pe by kt and x is equal to cos theta. So let us rewrite this. So px is equal to 0 to pi and then so we write p cos theta like this and then exponential of ux and 2 pi sine theta d theta divided by integral of 0 to pi e to the power of ux 2 pi sine theta d theta. So here 2 pi they get cancelled, and now so here we assume that x is equal to cos theta, then this dx is equal to minus sine theta d theta, and the upper limit is lower limit is x is equal to theta is equal to 0, x is equal to 1, theta is equal to 0. Upper limit x is equal to theta is equal to pi when theta is pi, x is minus 1. So the limits are px is equal to minus 1 to 1, and then we have p here, you can plug it out, and cos theta is nothing but x, and then sine theta d theta is dx, we have minus sign, this will be a dx, and then e power ux. Okay, so and now we have here integral of sine theta d theta is basically the minus dx, so this will be e power ux, and then we have minus dx, so the minus sign they get cancelled. So all that we have to do now is this integration part. So px is equal to p times integral minus 1 to 1 x e power ux dx divided by integral minus 1 to 1 e power ux dx. So this function is called Langevin function, but we will solve for this. So minus 1 to 1 x e power ux dx, we can write it as x integral of eux minus d by dx of x integral of eux dx. So this would be x e power ux by u minus integral e power ux by u dx. So this x e power ux by u minus 1 by u square e power ux. Okay, so the limits of this would be minus 1 to plus 1. So this is e power u by u minus 1 by u square e power u, and then minus of minus e power u by minus u by u minus 1 by u square e power minus u. So we have here this minus into minus plus, so we get 1 by u square e power minus u minus e power u, and then we have a plus sign, e power u minus plus e power minus u by u. So this is the numerator value, and then we work for denominator. So minus 1 to 1, and then e power ux dx. This is e power u x by u minus 1 to 1, e power u minus e power minus u by u. So now we divide this. So what was our average value of x component value? p times of so integral minus 1 to 1 x e power ux dx divided by integral minus 1 to 1 e power ux dx, which is p times 1 by u square e power minus u e power u plus e power u plus e power minus u by u. This divided by e power u minus e power minus u by u. Okay, so this would be okay. So let me check whether I have done correctly or not. Put this. So we have plus coming here, and then u square. Okay, and then minus into minus plus. Okay. Okay. This is correct. So here we get p times of minus 1 by u plus e power u plus e power minus u by e power u minus e power minus u. Okay, so this would be our cot hx. So this p times, we can write this as cot h u minus 1 by u. So this cot h u minus 1 by u is called Langevin function. So here we try to plot this Langevin function as a function of u. So when u is very small, the Langevin function tends to u by 3. So this we are plotting L of u versus u in the limit of u tending to a smaller value. So L of u becomes u by 3, so we get a linear function. However, at u is greater than 1, the L of u is constant. So here the function is constant. Now coming back to our x component of dipole moment, we have p here when u is smaller than 1 and the limit tending to less than 1. So the L of u becomes u by 3, where we know u is equal to E by kt. Sorry, Pe by kt. So this we can write as Pe by kt, and therefore the x component of dipole moment is P times Pe by 3 kt. So we get P square by 3 kt times E. And now we compare our definition of dipole moment. So the strength of this depends on the field that we apply. So the electronic the dipolar polarizability is alpha d, which is now p square by 3 kt, where k is Boltzmann constant and T is the temperature. So the total polarizability is due to electronic polarizability, ionic polarizability, and dipolar polarizability. So we know that this is 4 pi epsilon r cubed, and this E square by omega naught square 1 by m plus 1 by small m, plus p square by 3k. So where r is the radius of atom, and omega naught is the natural, the frequency with which the ions oscillate. And T is the temperature. Okay, now only dipolar polarizability depends on temperature. Almost all substances show this electronic polarizability, ionic and dipolar polarizability. But there are substances, for example, silicon and germanium, so where we see that there is only electronic polarizability. So the dipolar and ionic polarizability are absent here. Or insignificant. Now we look at this. The permittivity of a substance at optical frequency is only due to electronic polarizability. So the total polarizability in this case is only the electronic polarizability. Therefore, the Clausius-Mosatti equation turns out to be epsilon r minus 1 by epsilon r plus 2 n alpha by 3 epsilon, where now this alpha total polarizability is replaced by electronic polarizability, 3 epsilon naught. So we know where n is rho times Avogadro number by molecular weight. So therefore, so this will be m times rho and then epsilon r minus 1 by epsilon r plus 2, which is equal to Avogadro number, electronic polarizability, the permittivity in free space. So this is for permittivity at optical frequencies. Now we look at the variation of polarizability as a function of a frequency. So when the frequency is in the microwave region, so we see the dipolar polarizability dominant. So when the frequency is in IR region, the ionic polarizability is dominant. The frequency is in UV region, then electronic polarizability is dominant. So we look at as a function of a frequency, as we increase the frequency from 0 to dipolar polarizability, the dipolar polarizability is constant, but in the neighborhood of dipolar polarizability, the dipolar polarizability drops, and then as the frequency increases between dipolar frequency, that is microwave frequency, and IR frequencies, and then we see the frequency is constant, the polarizability is constant. Again, as we increase the frequency, so we only see electronic polarizability. So what is being plotted here? Here we are plotting the polarizability as a function of frequency. As we increase the frequency, the polarizability also changes, but between 0 to dipolar frequency, the dipolar polarizability is constant. However, in the neighborhood of microwave frequency, the dipolar polarizability falls significantly, and as we go on increasing the frequency beyond microwave to IR frequencies, we see that the dipolar polarizability is insignificant, and they just follow the frequency, and here in this case we see only the ionic polarizability between at a frequency that is actually corresponds to the transverse optical phonons of a substance. So this is IR, and as we go on increasing the frequency, the dipolar polarizability and ionic polarizability, they are insignificant because their masses are so high that they do not respond to the higher frequencies. So at higher frequencies, the electrons only respond, and therefore we see at higher frequencies only the electronic polarizability. So this is ultraviolet frequency. So what we have beyond this ultraviolet frequency, even the electron do not respond to the frequencies. So at optimal frequencies, only the dipoles and ions and electrons, they do respond, and when the frequency is much higher than what is required to let the dipoles and ions to oscillate, they do not oscillate, they just stay stationary, and at a required frequency only they tend to oscillate. So when we go beyond this ultraviolet frequency, the electrons also feels like heavier, and therefore they do not oscillate to the external frequency. So this I will stop here, and we can continue tomorrow.